Hello everyone. Hello and welcome to Lazy Talk 18. So we are joined today by Dr. Gerhard Holst, PhD Senior Imaging Product and Application Scientist at Excelitas Technologies. He earned his diploma in electrical engineering from RWTH in 1991, followed by PhD from the University of Dortmund in collaboration with the Max Planck Institute in 1994. So Dr. Ho spent 7 years at the Max Planck Institute from Marine Microbiology before leading the research and development at PCO from 2001 to 2021, where he spearheaded the creation of scientific CMOS imaging sensors. After Excelitas acquired PCO in 2021, he continued advancing high-performance imaging solutions like FLIM, SWIR, and sCMOS systems. So in this session, Dr. Host will show how scientific CMOS cameras and film means fluorescence lifetime imaging microscopy can elevate life science research from setup to meaningful data. So please welcome Dr. Gerhard Holst and let's begin these enlightening sessions.
Thank you very much for the nice introduction. Can you hear me properly?
Yeah, we can hear you.
Okay. So thanks for the opportunity to talk today about scientific CMOS cameras and as an addition to talk about fluorescence lifetime imaging. The first slide shows you kind of an overview of what I would like to present to you today. I would like to talk very general with scientific cameras as, let's say, compared to commercial cameras. So I try to give kind of an explanation what it is, show you a bit about history, and starting from the status in 2006 when the whole project about scientific CMOS started, then when the first results were presented in 2009 and status today, when you can, let's say, buy a blend of very different scientific CMOS cameras for your scientific research or quality control. I need or would like to discuss or explain some important performance parameters of scientific cameras, namely sensitivity or quantum efficiency, signal-to-noise ratio, noise, dynamic range, calibration, and cooling. Show you just the blend of applications of scientific cameras as we know them so far, and then I will switch topic to explain a bit more about how fluorescence lifetime imaging can be done and what it is good for. This includes some comparison between time domain and frequency domain FLIM and talking a bit about our camera system that can do this and show some applications. And if there is time, I'll show you an image of the headquarters of PCO where I'm talking from. So let's start about scientific cameras because let's say that's the topic I'd have to deal and work with since 2001 and even before as a customer of PCO. And my take on this is how to describe what a scientific camera is. Well, a camera that can detect very low light scenes such that all relevant information from the scene or sample can be obtained. Scientific camera is a camera certainly that can cope with high contrast in an image such that no relevant information is lost. Further, scientific camera is a camera that can record sequences sufficiently fast such that no relevant information is lost. And it is certainly a camera that has enough pixels or dexels such that all relevant details of a scene can be recovered. And finally, in most of the relevant scientific cameras that you can get at the moment, it is a camera that has an appropriate pixel calibration or correction regarding offset and gain and sufficient measures against temperature drift. So if you would like to, let's say, translate these requirements into parameters, we are talking about a scientific camera with a low readout noise, a high quantum efficiency, a large intrascene dynamic range, a high frame rate, a high resolution with a good MTF, modulation transfer function, and an appropriate pixel size. And maybe we're talking about pixel correction, calibration, temperature control. I mean, maybe the camera is actively cooled, or you have a digital temperature compensation. And if possible, you would like to have a combination of all of these parameters. In my opinion, this would be kind of a scientific camera. And that's maybe as well the reason why usually scientific cameras tend to be a bit more expensive than commercial cameras. It's not about the richness of our developments, but I can use, let's say, this timeline with the appropriate cameras to show you some changes in technology. So in '87, PCO started to develop image intensifier-based cameras. At this time, the image intensifier was the detector for catching very low light signals. And then immediately the CCD cameras came. These were the first pure digital sensors. At the very beginning, the digital signals that were read out from these type of image sensors were analogized. I mean, they were converted into TV signals to have a chance to look at them. And then mostly video recorders have been used to record the images and redigitize them. Only in the midst of the 90s, there were the first computers that were powerful enough, and they had these internal bus systems, and you can add a kind of a frame grabber that allowed the serial transmission of digital images directly into the computer. And this feature of having a camera with a frame grabber and reading out digital images directly into the computer to be able to store them, to process them whatsoever, this really made a big success in the history of PCO. So here you see a variety of different CCD-based cameras. And associated to this image intensifier cameras, I show them or mark them as second right now because they started with a CCD image sensor as a main detector. And nowadays, the main detectors are sCMOS sensors. The image intensifier is slightly difficult or is different from a normal image sensor because you have a two-stage system in always. You have a primary detector, which is the tube, and then you have an amplification process within the tube that generates a bright image on the phosphor screen, and this is by optical means imaged to a digital image sensor. Still, these cameras are available, but not for the reason of amplification of low light signal, but more for being the only cameras that allow exposure times down to the range of 3 nanoseconds. Well, at the beginning of 2000, millennium, the first relevant CMOS sensors came, but they were mostly used for high-speed cameras. So they were very fast in reading out the images, and the first high-speed cameras had about 600 frames per second, then at a resolution of 1.3 megapixel, and then newer developments achieved 2000 frames per second in full HD resolution and all of that, but they were quite noisy. So they had the real impact of offering high frame rate to do slow motion images or to observe fast reactions, but they were not exactly optimum for very low light signals. Then, along with the 2005, 2006 years, new concepts for CMOS sensors came to light. And this was the beginning of the so-called scientific CMOS image sensors. And they have more or less overtaken all of the representations of image sensors in scientific cameras. And then there were very specific and special sensor developments, namely here the fluorescence lifetime imaging, as well as new materials like indium gallium arsenide, which is sensitive above the limit of silicon. So that means above 1,100 nanometers, allowing to open up a larger spectral range. So you see on the timeline, there has a change from CCDs to CMOS, and this is reflected by, as well, the introduction of scientific CMOS. So as I said, in 2006, and I've given presentations at this time as well, and if I've been asked, I need a camera with a high image quality, then certainly I would have advised buy a cooled CCD camera. If there was a question for very low light imaging with a high image quality, well, a cooled electron multiplication CCD camera with this amplification process. If I would have been asked for a high frame rate camera, well, certainly CMOS, because CCDs, as you might know, is a serial readout process and therefore inherently slow. So you get maybe 1, 2, 3 frames if you have maybe 4 output amplifiers, then you might get up to 100 frames at 1 megapixel, but that's about it. And if you would have needed at this time the combination of low light, high image quality, and high frame rate and high resolution, it wouldn't be available. So that was the situation in 2006. Nevertheless, as usual, and usually, I mean, technology development is ongoing. At this time, 3 companies teamed up. So one company was Fairchild Imaging, who had some nice ideas for new image sensors. Then there was our competitors, at this time still under technology. Nowadays, they have been acquired by Oxford Instruments, and at this time, PCO. And we worked together, we teamed up and started a project to develop a new CMOS-based image sensor, which could accomplish all the combination of these requirements. And finally, in 2009, and this was funny enough because next week we have another Laser World of Photonics show here in Munich. In June 2009, a new CMOS technology called Scientific CMOS, or sCMOS, was presented to invited journalists along with the laser show. And there on stage were 6 people, 2 from PCO, that was the founder and owner of PCO, Dr. Ott, and myself. And then there was from Fairchild, Colin Earle and Dr. Boyd Fowler, who was the mastermind behind the new pixel architecture. And there was Donald Denver and Colin Coates from Andor. And we presented this new technology. We decided during the development process to call it different because the general perception, as I've tried to tell you, was if you want to have a high image quality, buy a cool CCD camera. And if you want to have fast frame rates, then buy a CMOS camera. But for the first time, now there was a CMOS image sensor available that outperformed the formerly shining CCD image sensor. Well, we had at this time already the EMCCDs, and they started to have a linear gain control as well. If you're familiar with it, these are standard frame transfer CCDs that added kind of acceleration and impact register at the output. So with a lot of very different higher voltages, they added energy to the charge carriers that have been generated. And with this energy, these charge carriers were able to hit the crystal lattice and generate more charges, like the amplification process in an image intensifier. And by this, you could, let's say, amplify the signal before it was read out. Therefore, you only have the standard readout noise of the output amplifier, but you can increase the signal before, which helps with the signal-to-noise ratio. In sCMOS, the ideas were really very interesting because in these typical structures of a single pixel, some of the capacitor values have to be minimized and such that you are minimizing or reducing the KTC noise that comes with that. And the second brilliant idea at this time was really to use two 11-bit AD converters instead of one 16-bit AD converters, because you can operate the 11-bit AD converter at a slower frequency, which minimizes the additional 1/f noise of the converters. So both of these measures generated image sensors that had a lower readout noise than the CCDs. They had a higher frame rate because they were CMOS sensors. They had a higher dynamic range and therefore generated the first image sensors in the CMOS range that have better performance data than a CCD. There were certainly some differences as well if you compare them to EMCCD. So the very first sCMOS sensors were, for some applications, a lot better than EMCCD, but still the EMCCDs were optimum in the range of, let's say, photon counting. But this has changed nowadays. This is an old table from this time in 2001, and this compares some of the principal performance parameters. Sorry that it's in German, but I took it from an old slide deck. So it compares the interline transfer CCDs. At this time, the Sony IMX285 was in very many cameras, doesn't matter whether from Hamamatsu, from Photometrics, from Andor, from us. All of them had the same sensor, 1.3 megapixel, 6.45 micrometer pixel size, maximum frame rate of 12 images per second, and a best possible readout noise of between 4 to 5 electrons. Quantum efficiency was okay. It was a front illuminated sensor. It was about 60%, and the dynamic range was 1 to 3000 or 3000 to 1. Now, EMCCDs had at this time 1 megapixel resolution as well, 8 micrometer pixel size, a bit larger, frame rates in the range of 30 frames per second, and due to the gain, a much better readout noise, so smaller than 1 electron. Quantum efficiency depended on whether it was a front or back illuminated. So the front illuminated were on par with the interline transfer CCD, same technology. And the dynamic range was, in this case, 1 to 8500. But if you increase the gain more, then the dynamic range is reduced, since you earlier fill out the pixels with the charges. So that depends on the, let's say, full work capacity of the readout register. So more gain always means reduction of dynamic range. Scientific CMOS there, the first sensor was 5.5 megapixels, so a significant amount higher resolution, 6.5 micron pitch, 100 frames per second, and the readout noise at the very beginning of smaller than 2. Later on, it was reduced to 1.2 or 1 electron. And depending, the first sensors were front illuminated. Later on, we had back illuminated as well. But it started off with a much higher dynamic range. And I will come to that later, where it could be good for. So Scientific CMOS, and this was the discussion of this project team, and this project within PCO was my project. We discussed all together how to make clear to the people that these CMOS sensors perform better than the general perception of CMOS sensors. And therefore, we called it Scientific CMOS. And this was really funny. Later on, I think 1 or 2 years after, as well, Hamamatsu had access to the first only rolling shutter sCMOS sensor. And with all the combined efforts of marketing, within 3 years, the people on a microscopy conference knew there are sCMOS cameras. They didn't know what it was about, but it was good. and this we achieved by not, let's say, securing the expression Scientific CMOS. It was free. Now, what's the status of the scientific cameras today? In 2015, Sony made a move and has sent this letter that you see here to the customers to inform the customers that they stop making CCDs. The production of CCD image sensors always has been more expensive due to the materials used. And since now, even in the very low light applications, the CMOS sensors performed on par or even better, Sony made the decision, they stopped making CCDs, and this had an impact as well. And since Sony at this time, and I guess they still are the major supplier of image sensors for the general camera market, people were now switching from the former Scientific CCD cameras to Scientific CMOS. And other manufacturers, in addition to Fairchild, like G-Pixel or Anafocus from Teledyne, started to make CMOS sensors with different ideas, but they approached similar performance parameters. Here you see an overview from today. As CMOS cameras made by either PCO, Hamamatsu, Andor, or Photomatrix, Teledyne, or Taxon from China, as well Ximea in Germany. And you can compare the, let's say, performance parameters by comparing the data sheets. To give you some examples of actual CMOS cameras, I just mentioned two of ours. So this is the PCO Edge 10BI based on a Fairchild image sensors, the LTN4323. And it has a resolution of 10 megapixel, pixel size of 4.6 micron, and a diagonal of 23 millimeters, which is helpful for the newer microscopes with the larger field of view. It has a readout noise of 0.8 electrons. It's a rolling shutter sensor, and it comes with temperature stabilization. To compare it to the former CMOS cameras, like, for example, here, the non-actively cooled Panda 4.2, due to the smaller pixel size, the vertical image is a little bit smaller than before, while the diagonal is a lot larger and you get more resolution. Then we have the new PCO Edge 9.4, which is the, let's say, sister or brother sensor from Fairchild. It's the HWK4123. And this is the image sensor, for example, that is as well in the Hamamatsu Quest 2. It has similar pixel size, a little lower resolution, but a much lower readout noise. But you pay the price of a lower dynamic range. So this is something that is defined by your application, what is more helpful for your imaging. The funny thing is, with this low readout noise that have not been thinkable before, we are in the range of 0.3 electron readout noise, which means if you look to the simulation here, and we assume Poissonian distribution of 3 photoelectrons per detector element, then these curves show you the envelope that is given in your histogram at different readout noise values. The fact that you are able to see the single filling status of the detection signal gives you more trust in the signal itself, because as far as you see these fingers, then you can be sure there are 2 electrons in that bin or 3 electrons. And you see, if you have a readout noise of 1 electron, then you get the typical histogram you might be used to. And still, it will not change the value, but you have a higher uncertainty, whether there are really 2 or maybe 3. Nevertheless, this helps you now to get the best possible signal-to-noise ratio for low-light measurements. And second is, now we are in the range that formerly has been, let's say, still occupied by EMCCDs. And I think this advantage of the EMCCDs now with these low readout noise values is gone, because now the major noise contribution in your signal is the signal itself again, which is the photon noise. But I've talked or used a couple of different expressions of describing different performance parameters. And I would like to explain and talk a little bit about them, just to give you some better feeling what is required for your application. Because maybe you don't need a low readout noise because you have enough signal, or you don't need a high dynamic range because you always have signals around a certain average value, so something like this. To start with, more than 10 years ago, the European Machine Vision Association has started a working group that developed kind of a quality standard. So that was an initiative to define methods how to measure, compute, and present these performance parameters. It's the EMVA 1288 standard. Over the years, there are different releases, and it has been extended and so on. And right now, as well, it will be turned from a European Machine Vision Association standard into an ISO standard. So currently, I think last year it started, and this is now becoming a more international standard. Nevertheless, over the 10 years, still, there were the corresponding machine vision associations from America, from the USA, as well from Japan, and they signed together with the EMVA a G3 contract, and later on the Chinese organization and another German organization agreed on that as well. In scientific applications, very often the people discuss or try to figure out how sensitive the camera needs to be and how sensitivity is defined. In our opinion, and this is as well the opinion of the EMVA, it's the quantum efficiency. What is that? Well, assume you have a semiconductor material where there is a light sensitive volume. Some photons are hitting this material. Then a certain amount of energy is lost at the very surface because it's reflected. Then part of the photon flux is entering the material, maybe some part is transmitted, and therefore there are quite a few different mechanisms where energy is lost in the process and is not contributing to your image. And this is described by the quantum efficiency. That means how much charge carriers you get from how many photons. Based on that, and this is as well described in the EMVA 1288 standard, manufacturers of image sensors, as well manufacturers of cameras, give you these nice quantum efficiency curves because they are not as sensitive over the whole spectral range. You see here from 300 to 1000 nanometers. This is a typical sCMOS QE curve of a front illuminated sensor because it's not larger than 60%. Nevertheless, if you are thinking about purchasing or defining parameters for a camera, you always have to think about that the image sensor is not the only source of a loss of quantum efficiency, but there is also an input window with transmission losses. Therefore, let's say the major scientific camera manufacturers, they offer the whole curve. So you get the transmission curve for the input window, you have the quantum efficiency curve of the sensor, and this is what the camera is doing. If you are not sure, you will have to look to the, let's say, description of the QE curves, if it's a pure image sensor curve, and if there is only this image sensor curve without the front glass, then you have to consider this because that's what you get if there is an additional glass in front of the sensor. How is the quantum efficiency determined? Well, in general, what is usually recorded is the so-called photon transfer curve. So at different signal quantities, always a couple of images are recorded, and in this graph shows the variance, so the difference between two images at the same signal quantity. And then you get the variance along with the signal, and if you fit a linear curve into that, then the shape of this curves give you the conversion factor or the inverse system gain, which means with that shape, you can convert the digital numbers of your images into numbers of electrons. And this is then compared at different spectral wavelength with a calibrated detector. And then you are able to get these in percent quantum efficiency curve. There's only one problem with that method. The shape gives you the conversion factor, which allows you to calculate back the number of electrons and compare it to a calibrated detector. Now, if the curve is not very linear, then it depends on your approximation which type of value you get from the shape. Because any change in the shape will change the conversion factor and will give you a different QE curve. Fortunately, there are some other possibilities to check whether what you are doing is appropriate. And one possibility is to use iron 55, which is a soft X-ray source. And if you position this X-ray source in front of your image sensor, then it's known that if some of these rays hit the silicon, they generate certain amounts of charge carriers. And now if you compare this, you can as well determine conversion factors, and we've done this for these three different lines, and you see that all the conversion factors are in a good agreement between 0.5 to 0.50 or to 0.49. And now if we compare this to the standard PTC method, we can prove, well, for the sCMOS sensors, it's quite safe. So that's fine. So we can continue. But if you have standard CMOS or let's say maybe cheaper CMOS sensors that don't have a linear PTC curve, you might have issues with it. Another important parameter is the signal-to-noise ratio. The better the signal-to-noise, the better the image quality is of your. And you see here different representation of fluorescence images of convallaria sample at different signal-to-noise ratios, 15, 10, 5, 2. Although even at the signal-to-noise ratio of 2, you might see some structures. If you compare the blow-ups and if you want to do image processing, it will be difficult, impossible to get information out of that. The definition of the signal-to-noise ratio is the number of photons divided by the total noise, which is, here you see the number of photons, and the photons themselves, since it's a statistical process, have their own inherent noise, the photon noise, and the readout noise of the camera. And depending on the size or the quantity of the signal, you could, let's say, simplify the calculations. So if there's a lot of photons, let's say 100, 200, 300, 500, then only the photon noise is relevant because it's a lot larger compared to the readout noise of the camera. But if you're in the low light regime, then certainly you have to consider the readout noise of the camera. From the time of 2010 and so on, we started to convert these or to compare these signal-to-noise ratio curves. And the best possible is just if you assume that you only have photon noise. So you can't get better than that. And then we have used a simple camera model and compared the SensiCam QE, which was a cooled interline transfer CCD camera. We had the EMCCD with a gain of 1000 based on an E2V, back illuminated sensor, CMOS, sCMOS, front illuminated, back illuminated, This includes different QE values, and we had a front illuminated Texas Instruments EMCCD. Now, these are the values that you get from the model, and then you can define something called single photon counting, a range of 1 to 10 photons. You can define, let's say, enough light range. This is deliberately taken at 500 photons. You can go even a bit smaller on that. And then this is the range where you see that some of the curves cross and become better than the others, the corresponding curves. And this is the low light range where the CMOS camera started to shine at this time, from then on. Here you see a typical signal-to-noise ratio curve that is demanded by the EMVA 1288 standard. And as well here, there is an absolute sensitivity threshold, which is when the SNR is 1, because below that you are not able to see anything, any sensible things out of your signal. And the dynamic range is, let's say, the saturation value divided by the sensitivity threshold. And I will have to talk through that in a few slides again. But now, and if you follow me and accept that the signal-to-noise ratio is a very important and interesting value for your applications, there is an issue because it's not alone. And you will see that here. We have a camera that gives this nice image of a tree. And this has certainly a signal-to-noise ratio. Now, if I take a second camera with larger pixel size, I get this. And obviously, because now pixels are larger, they are able to collect more signal. Therefore, the signal-to-noise ratio is larger than the first one. I think this is nicely understandable. If you go on with that, if you're looking for the best possible signal-to-noise ratio, then you could do this with that camera or detector. Now, this is the best possible signal-to-noise ratio that you can get, but something is missing, and this is information. Therefore, isolated, the signal-to-noise ratio is nice, but you need more than that. And you have to decide for your application what is more important. Let's talk a little bit about noise. Here we have two cameras, and they image one of the plants in my office. And if I blow up part of it, and I would like to ask you which camera shows more noise in the images, certainly, I guess most of you will say, well, the left one, certainly, because it's more granular, it looks more noisy. And you're right. Now, if I read out, it's still the same image, just part of this, just one line. And if I look at the values in the same scale, so the y-axis scale is the same, and if I ask again which camera shows more noise in the profile, certainly now, camera 2. You see the changes of the signal, they are much larger than on the left-hand side. What's wrong? Did I cheat? No. Everything is okay. It can be explained with an X, because if I read out the whole line and if I do appropriate min-max scaling, then you will see, well, left side, the signal is a lot smaller compared to the right side. Which means basically on the left-hand side, what is more dominant is the readout noise of the camera, while the larger noise on the right-hand side is more the noise of the signal itself. Let's say that's the good noise, because it's the photon noise. Basically, it was the same camera at different exposures. Just to give you a feeling, when you look to noise, you have to decide for your application what type of noise is relevant to you. Based on this, if I take a standard image out of my office towards the building on the other side of the street, and if I take two of these images under the same conditions, short time one after the other, and now if I do a calculations, what would you expect if I subtract one image from the other? I think if everything is very similar, you would expect, and this is, I would have done this before too, that it's black. But then you ignore the temporal noise of the light. Because the larger the signal is, the larger the noise becomes in absolute values as well. Therefore, you see in this difference image basically the same information like here, because different intensities give you different noise values. The only part of the image where the signal is 0 is where the image has been saturated, here in the white. So there it's black. We are out of noise, so to speak, out of the range of the camera. Finally, sometimes it also has to do with perception, because if you have looked to these two dark noise images, certainly I would like to ask you which camera you would select. Most of you would decide for the right camera, but the readout noise of the left camera is more or less half of the readout noise of the right camera. And this is something, even if the camera is calibrated, nevertheless, you will see, based on the structures of the CMOS sensors, sometimes these column structures. They are very, very tiny, but even though they become visible to the eye, because our brain is very sensitive towards repetitive structures. Therefore, here in the left-hand image, you had at an earlier stage would get sufficient signal-to-noise ratio compared to the right hand. And whenever you put some signal on that, some of these fixed patterns are gone. Nevertheless, if you simply look to the black or the background noise or dark images, this looks less, let's say, convenient, although it's the better camera. Another parameter that is important is the dynamic range, and I think I have to speed up a bit such that I can reach fluorescence lifetime imaging as well. Visually, we live primarily in an 8-bit world. So human eye is able to distinguish 255 gray levels. Printers work on that, PC screens, TV. Exception is radiologists. They say that they're able to distinguish up to 10-bit gray values. But nevertheless, why should I go for a higher dynamic range? And if you have a look to the next movie, and I hope it will, no, I've started it. You might see some changes. The car has switched on the light. This is a sequence that we have recorded with a color sCMOS camera out of our office towards the supermarket on the other side of the street. And it was in winter in the evening. And now you see full scale this film. Now it's replayed again. It's not a different recording. It's still the same data, but we use a different scaling for the representation to the screen. And you might be able now to see some more structures here in the shadow of these parking lots. And then it's replayed for a third time. And again, it's not new data. It's the same data, just with a different way of how to represent them, how to look at them on the screen. And now you can even read the sign plates if necessary. So why should you use a higher dynamic range? Well, the answer is more information. Because all of this was within the same recording. You might not be able to look to all of the information which is present in your data at the same time, but it's there. Here you see a different way of looking at this. On the left-hand side, this is the total scale. Then the second image shows a min-max. Then this is scaled to the lower signal. And this is a non-linear representation of this to be able to see at all the structures within one image. And this is as well based from the very beginning of sCMOS, so you are calculating the dynamic range just with the full well capacity divided by the readout noise, because still the readout noise was larger than the photon noise. This has changed now, and this is something I will have to point out, and we might want to change in the future our data sheets according to that, because nowadays, and there are these very nice low readout noise sCMOS cameras available right now. We have readout noise levels in the range of 0.5 or 0.3 or 0.2, which is nice, but you don't have signals that are as small. The smallest possible signal that you have is 1 photon. And since photons have their own statistical distribution, you have meanwhile to consider the photon noise as well. Therefore, we suggest to follow the definition of the dynamic range of the EMBA 1288. So this is saturation divided by the minimum threshold values. I mean, that makes sense because this is something that you can use. I mean, there is nothing like half an electron signal. I mean, it's very good that the readout noise is so low because you can trust your signal much better, and you get good images even when your signal comes out of the noise. But it doesn't make sense to use, let's say, a full well of 600 or 700 electrons divided by 0.3, because it's an artificial dynamic range that you are not able to use. So sorry for that. If still using by the old formulas to give the dynamic range, we will work on that and likely change it in the future. Finally, since you have seen all of these structures here according to each of the column, which is an issue of CMOS sensors, because each column has their own amplifiers, their own AD converters, and so on. Therefore, in general, a scientific camera is calibrated, and this is done by a linear operation. Therefore, you can remove most of the offset differences, and you can remove the gain differences, and this is done properly by the manufacturers. Further, since there is, let's say, an assumption that cooling is always good, which is, yeah, the temperature control is very, very good for a camera, because then the image sensor is happy and always sees the same temperature. It doesn't change, no offset drift and so on. And therefore, the temperature control is good. A reduction of dark current noise is good by a deeper cooling, because then you have less noise contribution by the dark current, which is temperature dependent and dependent on the exposure time. But you have to consider that the cooling will change for the near-infrared signal, the quantum efficiency, and quite dramatically if you go up to 800, 900, or 1000 nanometers. So this should be kept in mind. If you are using cameras in that area, then the deepest possible cooling might not be such a good idea, because you lose quantum efficiency. Just some applications of scientific cameras you might know or might not know. All of the more modern microscopy methods that try to increase the resolution to see more, even on a molecular level, they use sCMOS cameras, so single molecule localization. This is an example from Leica Microsystems, where we teamed up in a research grant. It's possible with sCMOS cameras. Then you have as well here a size system with a size ELIRA. There is an additional lattice SIM applied, and you can get super resolutional images with sCMOS cameras. Here you see structured illumination by itself. In these applications, there is additional information added to the illumination, to the excitation of fluorescence. And since you know these additional information, by calculations, it's possible to recover the information from the focal plane better, as well to increase the resolution above the diffraction barrier. In this case, it was a larger microscope by General Electric, the OMX Delta Vision system, and here you see the improvement in resolution. And a more recent example on a university-based SIM system you see here from the transient microscopy in 2025 in Germany. On the left-hand side, you see the wide field deconvolved image, and on the right-hand side, the SIM image. And from the original 2000 by 2000 pixel, you are able to create a 4000 by 4000 image. This has been obtained with one of our edged MBI. The only method that is available for living cells, because less light, is light sheet fluorescence microscopy. There are the commercially available systems from Zeiss, which are very, very nice. Then there are the non-profit propositions of the Flamingo system you see here, which is equipped with some of our cameras. And this is fascinating because the organisms survive this for days. So this has the lowest possible phototoxicity. Nevertheless, you can use light sheets as well for different applications. Here it's more physical, for imaging of scattering particles in any flow situation, either in air or in water. And you can calculate from there very efficiently flow. You can use more cameras to get a more three-dimensional results. And here, this is an example of the flow situation around a propeller. And these customers have created and measured very nice three-dimensional flows. Other applications include wind tunnels. So this is more the scientific stuff. And I see from I think I have some about 10 minutes left. Is that correct? Okay. I don't hear nobody, but I assume I'm right. Let's talk about fluorescence lifetime imaging.
You can extend.
Pardon me? I couldn't hear you. Can you repeat this, please? Hello?
You can take your time to finish. Okay, no problem.
Okay. The second part is about fluorescence lifetime imaging. And you might know from your fluorescence applications, I mean, you see here the typical energy level scheme for photoluminescence, which includes fluorescence and phosphorescence. So you have absorption of energy of some molecules. They get excited, which is not favorable for them. You have some conversions of energy within these, changes from a higher energy level to a lower energy level. So you are converting part of your energy to vibrational energy or temperature energy whatsoever. And finally, since the excited state is not favorable for the molecule, it returns to the ground state by emitting of light. Since you have taken some energy for other processes, the emitted light favorably has a lower energy and can be separated by optical means. That's the basic, let's say, principle for 90% of all optical microscopy applications, I guess, for biomarkers and so on. Now, this usually is an intensity-based method, but this process has an additional parameter called decay time or lifetime, which describes the amount of time it takes, it remains in these excited states. I skipped to show the intersystem crossing or the spin conversion that is basically taking place if you have phosphorescence, but let's say from the outside, phosphorescence just has longer decay times or longer lifetimes. Now, if I would like to measure this as an additional parameter, as a further source of information, I have two options. One is I can do this in the so-called time domain, which is, you see here on the left side. So this is the excitation light pulse. Or I can do this, technically speaking, in the frequency domain, which is and has the same amount of information, but is a different approach. So in the frequency domain, instead of having a single pulse, we are using continuously modulated light. Now, if I do so, then this is the reaction of the fluorophore. So you have a rise, you have a decay, and in frequency domain, it's not so obvious, but you have as well kind of a delay, and the amplitude changes and maybe the constant part as well. In frequency domain FLIM, and I explain this because that's something that we are able to do with a camera, we would like to measure the amplitude. I mean, you see here the blue signal is the excitation, the emission is the orange signal. I would like to determine the ratio of the amplitude towards the constant part, and I would like to determine the delay, technically speaking called phase angle. And both of these, the ratio and as well the phase angle, have a relationship towards the lifetime. So that's a possibility of how to determine the lifetime. If I want to do so with a fluorescence signal, then certainly from the sampling theory, I would like to measure certain points of this curve. And if I translate this to imaging, then this looks like integration windows for an image sensor. The issue is, if I want to go to very short lifetimes, which are very common for biomarkers or endogenous fluorescence, so in the range of nanoseconds, then the issue is I would need exposure times that are as small. And this is something, unfortunately, that is usually not available, because the shortest possible exposure times that are available at the moment in CMOS cameras are in the range of 120 nanoseconds. This would make measurements of nanosecond lifetimes quite cumbersome. Nevertheless, if you could do so, then in practical means, because in most cases, one integration is not enough signal, so you would repeat this, and then you change the onset and integrate, and so on. In 2007, we started a research grant based on a TOF, time-of-flight CMOS image sensor, together with a research facility in Zurich in Switzerland. And they developed for us a specific CMOS image sensor that can do the following. Well, if I look to one dexel or pixel, then each of these pixels has a light-sensitive area where you see here the emission is hitting it and generating charges. And with an external voltage signal, I'm able to control if these charges are collected in the left or in the right tab. So if I change polarity, then all the charges are collected on the right tab. And these structures are all over the whole sensor. So I'm able to integrate part of the signal that comes into tab A and the other part to tab B. Now, if I want to start with a certain position, then this would be a phase angle of 0. Subsequently, this has to be 180 degrees. And I can do it as fast as this modulation is. Now I can repeat this. If I shift the onset of the integration by, let's say, 90 degrees, then certainly the integration value that is in the first window is according to 90. Subsequently, the second window then is 270. By this, I would be able to integrate and measure the sinus signal that is coming from the molecule, from the sample. In addition to that, since this image sensor is not perfect, there might be a slight asymmetry between the recording of the two tabs, but I can overcome this by adding 2 more double images and shifting the onset for the integration by 180 degrees. In this case, the 180-degree information ends up in tab A, while the 0 information ends up in tab B. Now I can simply average from the former image these values, and then this type of, let's say, additional noise is gone on cost of the max frame rate. We've made a FLIM camera out of that. And meanwhile, since 1 year, we have a second version of it where we have improved and learned how to better cool the camera. And these are the parameters that we are able to have. It's still the same image sensor, so it has 1008 by 1008 pixel at a pixel size of 5.6 microns. Maximum frame rate is 45 double images. We have inbuilt modulation, a frequency generator that is able to send out these modulation signals to a light source and at the same time send the same signal to the image sensor. It can take external modulation frequency. It has a not so overwhelming quantum efficiency, and I explain the reason for that. If you want to switch that fast, these charge swing in each pixel, then the pixel itself, the light sensitive area, which is basically as well a capacitor, could not be too large, because a large capacitor is a shortcut for high frequency signals. Therefore, the fill factor of each pixel in this image sensor is quite poor, because I cannot increase the light sensitive area too large. So the real fill factor is about 16% only, and this is compensated by the addition of micro lenses. So the light that falls onto each pixel is more or less focused towards the small light sensitive area. So the maximum quantum efficiency is only 39%, and since we are in a fast operation mode, the readout noise is still quite large. It's not exactly sCMOS. Nevertheless, we are able to have about 10-bit dynamic range. The fascinating thing is the measurement of a lifetime distribution of fluorescence lifetime distribution is relatively easy if you look to the system. So you have the camera. The camera controls a light source. The light source is coupled into the microscope. So let's say the epifluorescence input, where the illumination takes place. Fluorescence is excited, and the emission is guided to the camera with the standard pathway of the wide field microscope. And finally, everything is evaluated by the software. Certainly, you will ask, well, what type of modulation frequency do I need for a certain range of lifetimes? Well, you can do mathematics a lot. Basically, if you have a range of lifetimes, then this gives you the optimum modulation frequency. And if you have a single lifetime only, then you can start with that. I warn you, because in 1 nanosecond you would need for an optimum modulation frequency 160 megahertz, and this cannot be done by the camera. But still, you can measure good results at 1 nanosecond lifetime range. But this means that the signal is not at the optimum position. And the optimum position, and unfortunately this is kind of mathematics, the relationship between phase angle and lifetime and frequency is a tangent function. That's the mathematics behind. So this gives you optimum modulation frequency, but even in non-optimum, you can get good results. So we did all of the measurements around 1 nanosecond at 30 megahertz or 35 megahertz modulation frequency. Having such a system, you need to do referencing measurements, and those people who have applied already TCSBC, so time-correlated single photon counting, they know they need to determine the instrument response function, and this includes the pathway of the light, because in 1 nanosecond light travels 30 centimeters, and you have quite a lot of these 30 centimeters in your setup. Therefore, you need to, even for frequency domain, you need to determine the zero phase angle. And for that purpose, usually you have references. So you can use any fluorophore, any liquid whatsoever, where you are confident and where you know the lifetime and which fits spectral-wise to your application. Another possibility, and we've investigated these type of dyed plastic windows in a metal slide made by an English company called Starner. Stana Scientific, and we checked these different standards that they made for intensity measurements, and they are quite useful even for lifetime measurements. So if we assume a mono-exponential decay, we did some measurements with the TCSPC system. It looks quite good, and I have one of these references, and I'm using it now for 5 or 6 years, and it works nicely. So that's a possibility. Another reality thing is that the sensor is not in total as ideal as I would like to have it. And here you see the modulation index, which is the amplitude divided by the constant part, and the phase angle, along with the intensity at 30 megahertz modulation frequency. And this is a measurement of the fluorescence reference. It should be a parallel to the x-axis. It's not. You see the measured dots, and we have such a curve, which is a model that we are fitting to it. And now if we do a reference measurement, in reality, we are not doing only one, but we are covering the whole intensity range. And if we do so and correct the values, then this is the precision that we are able to achieve with the modulation index and with the phase angle. So best possible, we are plus minus 100 picosecond precision for a mono-exponential signal. The workflow is as follows. You are taking raw data. From there, you are able to calculate intensity distribution. So that's the fluorescence intensity. You get a modulation index distribution, and you get a phase angle distribution. If you add the reference measurement, then you are able to convert both of the modulation index and phase angle into lifetime distributions. If you look to the book of fluorescence spectroscopy by Joe Lakowitz, you would see both have a pathway to the fluorescence lifetime, but you cannot combine them. Which means for your signal, if you're measuring at one frequency, and if the results are very similar, then you can be sure it's mono-exponential. If they're slightly different or accumulatively different, then unfortunately you have a multi-exponential decay. And depends on your application whether you need to investigate this further or not. Another possibility is with a reference modulation index and lifetime distribution, you can create, because now per pixel you have two values, you can create a vector. A length of the vector is the modulation index, and the angle towards the x-axis, the phase angle. And then you can get these phasor plots, which is a different representation of the same values. And these can help you to separate parts of your images, to differentiate, and so on. How to use these type of cameras? Well, we have the camera, but this is only able to control the camera and store images, but it doesn't do all the reference and corrective calculations. We are working on our own software, but it will take some time until we have it. Another possibility is to use, because we teamed up with the people from Nikon, and they have developed a PCO FLIM module for the Nikon microscopy software. And with that software, it's quite easy. You can do the reference measurement, you can do the background correction, and you get all the results, and you get phasor plot feedback and all of that. They have different control tabs, and they developed this together with us, and yeah, that's very convenient. Further, and this is something, again, if you are interested in the range of a few nanosecond lifetime measurements, then you need light sources that are fast enough. I know that you can buy from Tor Labs and others LED light sources that claim to offer 100 or 200 megahertz modulation capabilities. And we've checked. We have checked as well 60 different brands of manufacturers of LEDs. They are not fast enough. You get some modulation, but on a large background, and the background doesn't help you with the signal, it just burns the sample. So if you need to measure in the range of 1 to 10, 20, 30, 40 nanoseconds in that range, then we advise to use a laser. Now with a laser, the wide field illumination might seem to be a little bit cumbersome due to the speckles, but this can be solved with the addition of a liquid light guide. So we use this for wide field. But we can as well couple into single mode fibers for use the illumination for light sheet or turf or spinning this stuff. We've teamed up with Omicron. They make these lasers for us, but you can use any laser that is able to accept the modulation signal from the camera and the dark gate signal of the camera. For the adjustment of the laser, we are using the Omicron Control Center. Now let's go for some applications. One obvious application is first the resonance energy transfer, because it's much faster if you are able to measure the lifetime of the donor than doing the total process of measuring intensity of the donor and then bleach the acceptor and measure against the intensity of the donor. Here you see some hex cells that were carrying some indicators, some FRET indicators, and the shorter lifetime shows you the cells where FRET happened, while the yellowish ones, no FRET happened. We have some other applications, meanwhile, with the biosensor for cancer detection. This is one of our customers. They have a very nice biosensor, gives you the readout in lifetime, and currently they are developing their own instrument based on our camera, where they can use their biosensor for the early cancer detection. A wide field of applications for fluorescence lifetimes is certainly optical chemical sensing, most prominent oxygen sensing, because you have to calibrate these sensors for the concentration of oxygen. And if you once calibrate and change then the light field, you will have to recalibrate. But for the lifetime, it doesn't matter whether you are illuminating 100 or 1,000 molecules, as long as they have the same lifetime, you get a useful signal. So for calibration of optical chemical sensors, in many, many applications, the fluorescence lifetime is a more convenient parameter. You see some results from oxygen measurements, compared the frequency domain PCO FLIM versus the old time domain sCMOS sCMOS. And this is the oxygen distribution along of marine grass roots. And yeah, more or less this covers 25 years of my scientific work as well, because the sCMOS sCMOS only exists because I did want it at the time as a customer from PCO. You can do pH measurements with planar optodes as well, as long as you have an indicator that changes the lifetime, which not all of the pH indicators do, but there are some. And then you get two-dimensional readouts of the pH distribution, so that's nice as well. And you can use the FLIM camera with the spinning disk system, but you have to be careful, since unfortunately the optical output of the Yokogawa systems, of the newer ones, the CSU-W1, they expect EMCCD sensors, which have a large pixel size, and they have no possibilities, as far as I know, that to reduce or change the optical output. Therefore, you are throwing away a lot of light. And in most applications where we tried this, the camera seemed to be not sensitive enough, but it was more the optics of the spinning disk system. Here we have a Crest Optics X-Lite V3, and certainly you get a better plane resolution of your values if you use the confocal. You see here as well the lifetime distributions of the wide field compared to confocal. And but you have to live with the differences in signal, because in a spinning disk system, usually you are losing a lot of light. So here you have an exposure time of 80 milliseconds, while on the right-hand side we had 800 milliseconds. Another application here of some oxygen sensors at the University in Münster was quite nice, because they were able to get a good time-lapse readout of their oxygen sensors on cell level, even at very low signal side, and they will publish about their results. So that was very nice and very convenient for them, because they could hook the camera to this larger microscope system with the incubator, which is in their lab, it's not possible to do it with a scanning system. There are many potential applications of fluorescence lifetime imaging, starting with FRED, optical chemical sensing, whole slide scanning, maybe microplastic detection, cancer research, brain cancer therapy, new solar cell materials because they show a significant photoluminescence that depends on the mixing components of the perovskite with the silicon and so on. We had some applications in wood sorting and 3D pathology. Well, I'm near to the end of my presentation. I'm talking to you from this place there, the headquarters. So I'm sitting here in this corner. And that's a nice area in Germany, in the southern part. And I'm with Excelitas PCO. And we hope to develop and make high-quality scientific cameras that help you to answer your questions in research or quality control. Thanks a lot for your attention, and I'm open for questions. And I think I will stop the... Let me have a look. So, and
Thank
sorry
you.
that still my camera is not operative, but yeah. I hand over back to Aditi.
Hello.
Yeah.
Hello, thank you so much.
Yep.
Yeah, so we have questions. So the first question is from Dr. Prasanta Kumar Datta. And the question is, does every pixel record spectra just like hyperspectral cameras apart from time-resolved imaging?
If I get the question right, well, every pixel is sensitive over a certain spectral range. So if we talk about most of the sCMOS cameras, there are these typical QE curves. So you can record from 300 to 1000 nanometers at different QE values. There are some back illuminated image sensors that even open up sensitivity down to 2 nanometers. So we have some of them as well. If you want to do hyperspectral imaging, then usually the area type of image sensor is converted into a line sensor, because then in one direction you're obtaining the spatial information, and in the vertical direction then you get the spectral information. But if you then want to get the hyperspectral information for each point in your sample image, then you will have to move the camera or the sample. Does that answer your question?
Yeah, thanks a lot. Thank you.
Thank you so much.
Regarding the time domain and frequency domain, which one do you think that gives better resolution in lifetime measurement?
Oh, that's a tough one. At the moment, if you need to recover multi-exponential information, it's still faster and easier if you use one of these TCSPC scanning systems, because at the moment our camera in principle can do it, but we don't have the software to do multi-frequency. Because if you want to get the same information, you will have to repeat the measurement at various frequencies and then resolve and get the information of each of the lifetime components out of it. If you have if you can live with let's say, apparent lifetime mono-exponential decay, then the faster thing is to use, for example, our camera. If you are in an absolutely low light level regime, like for example some of these voltage sensitive dyes, then still scanning, or some of the maybe in the next years upcoming spot array based cameras can do it, or if you have a still image intensifier, it's difficult. because the results are quite good even with our camera, but it depends on your application. If you really want at a high level of confidence, compare the different lifetime components, go for a TC-SBC system at the moment.
Excellent. Thank you very much.
Thank you so much. We have another question from Sandipta Ranjan Sahu. And the question is, how high QS is...
Well, I can read the question here. My question is, Sandipta here. You have a high quantum efficiency sCMOS camera, and it is an alternative to EMCCD. So I would like to know how you can compete with EMCCD camera.
I would say at the moment that we are on par with the MCCD cameras, but the problem will occur in the setup.
Mm-hmm.
And this has a little bit to do with the larger pixel size of the MCCDs. Mm-hmm. If you have your output optics from your microscope or from your system, like a Yokogawa system, then from the Yokogawa system, you cannot reduce. I mean, you would have to collimate or focus more, not to lose light. And then the difference feeling in, let's say, sensitivity is more based on a geometrical thing. Because if you increase or make the area of the pixel smaller and you don't change the photon density in your plane, then it will look like that always the camera with the larger pixel seems to be more sensitive, but this has nothing to do with the sensitivity. If you compare the EMCC right now with one of the actual newer sCMOS sensors that have readout noise values of 0.5 or 0.3, go for a sCMOS. It's cheaper, easier to handle. You get more resolution, higher frame rate, but you need to consider maybe change of your output optics if you are currently using a MCCD camera. It's not just you exchange the camera and that's it. Because it's clear if you have a 12 micron pixel and now you have a 4 micron or 4.5 micron pixel, then
correct.
You get less signals and you will have to either more collimate the output signal or use different output optics to adapt for that. But then I would say I would always use a sCMOS camera right now.
So that means in almost all the application in which an EMCCD camera is used, it can be replaced with your sCMOS camera.
In almost all, I would say yes, but certainly I would have to have a look to the application, because it can be that for longer exposure time. So if you have a low light signal and you need to wait until you have collected it, or if you need, for example, bioluminescence, sort of that, or chemical luminescence, then still the EMCCD, because it's a CCD sensor and they tend still to have a lower dark current. Because then you will have to see whether you can use the sCMOS camera at a very low light, very low temperature or something like this, because still CMOS has higher dark currents. That's a fact as well. So if you have long exposure times, you might want to stay with the MCCD still.
Okay, so that means in the longer exposure time related application, still EMCCD can be preferred.
Yes.
Okay, got it. Thank you.
And as I said, you need to have a look to the application. There's not a general answer to that. I think for most of the applications, I would say they can be done now with sCMOS, because the sensitivity is in the range of photon counting.
Yeah, got it. Thank you. Thank you, Dr. Ghosh.
You're welcome.
Thank you so much. Do we have more questions? I think we do not have any questions. Thank you so much, Dr. Gerhard, for the informative webinar.
Well, if you are interested in more information on the FLIM stuff, there is on YouTube. If you are Google hands-on and PCO and FLIM, there is a 30-minute video that shows how a measurement is done with all the referencing, and again with more details the technology is explained, because that was a compromise according to the available time.